This talk actually was inspired from a talk last year by Victoria Seek on Bayesian adaptive design. So some of you may have attended that and might remember some of the concepts here. All right. Is that true? All right, so some of the motivation here. Obviously, we know that some of the experiments we actually test are often very expensive, very destructive. And so the sample sizes we have, are going to be in a small number. Therefore, the tests that we do have to be, we have to maximize the information we get from those. For example, in the bottom left here, when we're testing these semis to carry the nation's stockpile around, we can't just go crash 100 different semis to get test data from. So we really want to maximize the data that we have available. All right. Okay. So just a quick overview of Bayesian adaptive design. So traditional design of experiments, these are things that are done statically. This is where you design your test beforehand. You have a specified power that you'll reach, and you wait until you collect all your data, and then you run your analysis at the end. It's great. It's predictable. You know the statistical properties, so it's a traditional way of doing it, and it's what's often done in the past. Bayesian adaptive design of experiments is more dynamic. So this is, you might change the experiment in real time. You might change the sample size. You might change some of the factors. And one of the things that specifically I'm going to talk about here is it allows the possibility of early stopping. So again, you might have a limited number of resources, and you might want to stop your test early as to not use up all your test units, especially if it's destructive testing. Okay. And I'll say actually that if you're worried about statistical power, Bayesian adaptive design can also deal with this. So you don't have to worry about losing the idea of power. And so kind of a thing to think about is, let's say that you ran 15 tests and you somehow knew that there's a 99% chance that you would conclude something had you performed, if you finished the 20 test series. Then why wouldn't you stop after those 15 and say, well, 99% is pretty likely. Why should I do an additional 5 tests if I know what's going to happen at the end of that? And that's really what this early stopping idea gets to. It turns out this 99% is not just some number I'm pulling out of a hat. This is a number that actually is calculated through a Bayesian model. So what I'm actually going to be talking about is assessing the robustness of this. So if we stop a test early, we want to make sure that it was a good idea. And so with a Bayesian model, we have a specified model in place. So how do the effects of it change as your modeling assumptions are not accurate? So specifically, it's assessing the robustness of the model. So if your model thinks data, for instance, looks normal, symmetric, and unimodal, how does it respond if it actually sees data that looks like this? Will your early stopping decision be a good idea, or will it actually give the correct result if the data that you see doesn't match your model? Again, in a high consequence situation, that could be pretty significant. So some of the technical details of a simulation that I ran, it's a very simple model. The thing we're actually interested in is a reliability requirement. So, what's the likelihood that your widget or whatever is within spec? What's that probability? I'm saying that I want my reliability to be at least 80%. The number, the predictive probability or the stopping rule, this is the thing that says there's a 99% chance that you would conclude at the end of the test this had you actually finished the test series. Okay, so that's really the number that's of interest. You could create some stopping rule to say, if that predictive probability is greater than some number or less than some number, test the stop early and conclude success or conclude failure. To do the actual robustness study on the right side of this slide, just kind of give some of the things I looked at, some different distributions, sample size, maximum sample sizes, whether outliers were there, and also the true reliability probability. So, right, I'm checking for, is it greater than 80%? So what I'm calling the effect size is the actual reliability number that I'm simulating data from. And because it's adaptive design, I'm basically reevaluating this predictive probability after every additional 5 samples, after collecting the first 10. So just here's a simple illustration of some of the results. So what I'm showing here is basically on the y-axis, it's an accuracy number that is checking whether you made the correct stopping decision if you stopped early. Okay, so you decided to stop early, 1, and 2, you concluded you made the correct conclusion for stopping early. So you stopped early and concluded success, or you stopped early and concluded failure. Okay, and then on the x-axis, it's just that's the true reliability number that I was simulating. Recall the 80% is the number I care about. That's that black vertical line. And so what this is showing is some metric, what I'm calling accuracy, for 3 different distributions of the true data generating mechanism. And again, you can see as it gets away from 0.8, overall those accuracy numbers gets higher, which makes sense, right? Because that's basically saying you're in the situation where either the first few tests of the series are showing basically catastrophic failure. And so it's very clear that your test is not going well, or the opposite, your test is going very, very well. And it's very obvious that I'm not going to use my units. But as you get closer and closer to the number that you actually care about, the accuracies are actually a little bit lower, which is in some ways, it can be a little bit concerning, right? Because you don't want to make the wrong decision. Okay, but the real point of this was to check some of the robustness. So like there's 3 different distributions on there. And there are some interesting trends that kind of happen in this plot. I'm not necessarily going to talk through it now. You're welcome, to talk later at the poster, and I have some other figures that you could look at. But it is really interesting, right? That when you're, for instance, in this case, the reliability number I care about, 80%, if the true reliability number, right, that you're trying to measure is close to that, then this method is, I mean, in this situation, right, given the wrong answer a good amount of times, which is concerning. However, at the very least, there are cases where when we do testing, it seems like maybe there's an obvious answer, you're halfway through the test, but your statistician's like, no, we have to complete this full factorial, right? Because we want that statistical power number, and that's the only way we can do this analysis. And so I kind of see this Bayesian adaptive design as a way to help mitigate those scenarios where it's like the final answer is obvious. Why can't we stop? Because previously, again, we couldn't keep that power number valid. But now this is kind of an approach where we could still say we have the valid power, but also we might be able to end the test early. So I'll just kind of, I guess one thing I didn't mention was there's 2 plots here for different maximum sample sizes. And you'll see there's really not a whole lot of difference between these plots. And I won't go over why that's necessarily expected right now, but feel free to bring it up later, and I'm happy to chat more about it. But so the overall, again, takeaway message is that early stopping using this Bayesian adaptive designs, I think can definitely be usable in these cases where there is a very clear effect, and that there's a very clear effect size, and it's very obvious kind of what the answer is, and we can stop that test early while still maintaining our desired statistical properties. Okay, so I'll end right now. Feel free to stop by the poster later, or chat whenever, and I'm happy to talk more. Thanks everyone.